Okay, so we're to the ideal gas law, which I presume you guys basically know, but we'll just do it right. So what we have are three laws that were established empirically, the so-called gas laws. We have Boyle's law that P is inversely proportional to V, the volume, Charles' law, and the law of Gay-Lussac, which say that respectively volume and pressure are directly proportional to temperature. And of course, each one of these holds the other three constant. So we're missing something, of course, because you guys know Pivnert. And the final question is, what would happen if we actually change the amount of stuff in the cylinder itself? So here I have a container full of, let's just give it a name, call it argon gas. And then I leak argon gas into this contraption. The piston is free to move. And I'm going to do it slowly, and it's a uniform temperature outside. So I'm doing this on like a, in a nice cool spring day where it's exposed to the atmospheric temperature. So that means that P is fixed or constant, and so is T. So the two variables that we're controlling and looking at the response of is basically we're changing the number of thingies in the cylinder. So I'm going to go right ahead and call it mole number. So we'll just say this is the amount of stuff. And we'll start with moles, and then we'll turn it into number of molecules. So units of this would be moles. And then what we're going to do is see the effect on the volume. So N versus V. And it turns out the last piece of information we get, which is Avogadro's law, is that the more stuff that we put into the cylinder, the bigger V is. And no things means no volume. So that actually does go through the origin. Okay. So that would be our dependent variable. And we have the last of the gas laws. So Avogadro's law. Which says that moles are proportional to volume, and this was done with P and T constant. And you know what? Retroactively, we didn't say it, but it's actually true. So for all of these, the number of particles in the cylinder was held constant. So we can go back and add that. And until we add entropy, these are the complete set of our thermodynamic variables. So PV and T. And now we're ready to just kind of realize that we have the answer. So we can rephrase Boyle's law by saying not that P is inversely proportional to V. We can say that PV equals constant, some constant. But then I can also say that P equals some different constant. So we'll call this constant 1. Times T, but then I can say that V is some constant times T, but then I could say that mole number is some constant times V, but I'll do that in the way that puts all the stuff on that side. So just kind of looking at this, what you end up with is, clearly PV, left-hand side. There's T and there's N over here. And there's one constant left over. So we basically can eliminate one of these things. And we'll call it R to start with. This is the ideal gas law, the mole version. And the new constant that we introduced, R, is the so-called universal gas constant. Which has a value of 8.314, whatever they need to be in SI units. So this would have Kelvin downstairs, moles downstairs, mole, Kelvin. So remember, we're now using absolute temperature, so we can actually phrase these with ratios. And then on what's left over has got to be pressure, which I'm going to do this as kind of a sidebar. So pressure would be newtons per meter squared. And then volume would be meters cubed. So we do get some simplification. And you might see this as actually pascals meters cubed, which is totally fine. Or you might see this as 8.314 Newton meters per mole K. Or you might remember from mechanics that Newton meters is joules. So you most likely will see it with this unit, so joules per mole K. So all of these are R. I think this is probably what most people use, the joules variant of this. Okay, and just as a quick reminder, what are moles, which you probably know. Roughly speaking, moles are a unit that lets us talk about small accessible numbers of amounts of gas. So basically, 1 mole of N is about a gram. And it's got a more precise definition, but for us that's good enough because we're going to actually go to numbers of particles. So okay, which would mean, and this is what we'll do more likely, is 1 mole of hydrogen gas, because that's H2, is about 2 grams. And then 1 mole of carbon, which has 6 nucleons, would be 6 grams, and so on. So we'll do a couple of problems with that, again, to remind you guys. Okay, so I didn't have to use moles. I could have used this in terms of particle numbers. So let's define N to be the total number of particles in the gas. So molecules are atoms. Atoms if it's like argon or something like that, or helium. And molecules if it's nitrogen or hydrogen or oxygen. So the only thing that you do if you want to phrase this in terms of particles instead of moles is it just changes the gas constant. So instead of PV equals little n RT, what we do is we multiply by Avogadro's number, which is the number of particles in a mole. So the number of moles times Avogadro's number is equal to the total number of particles, but then to multiply by something and not change our expression, we got to divide by the same thing. So to turn this into n, that's what that is, the mole number times the number of particles in a mole. We've got to divide the universal gas constant by Avogadro's number 2. So where Na is 6.02 times 10 to the 23rd particles per mole. And that would make this thing R over Na, which is defined as Kb, called Boltzmann's constant. .308. How far do I go with that? As far as your book, we'll just call it 38 times 10 to the minus 23 joules per Kelvin. And the Boltzmann's constant kind of physicsy version of this is PV equals NKT. The subscript is optional. Sometimes you will see NK, sometimes you'll see K sub B for Boltzmann's constant, but either are okay. Okay? And remember all of this, so the choice of variables you have is to do things in terms of mole number. So, if I have a handful of stuff, it would be a handful of moles. If I have a handful of stuff, it would be just like a ludicrously astronomical number of individual particles, like 10 to the 25th for a handful of sand. So this is the choice we have. We have either mole number or actual particle number, and you just got to pick the appropriate constant. R for mole number and K, Boltzmann's constant, for particle number. The choice that you don't get to make is you always use Kelvin for this. You need to use an absolute temperature scale. Okay. And we'll explore the units that you can get away with, the latitude that you do have, by just doing it in a problem. So 1 bar is about 1 ATM, and in normal SI units, that would be 101.3 kilopascals. And the question in some sense is, let's say that I went into space, or actually not into space, into just like a empty room, which was at standard temperature, 20 degrees Celsius. And I let all of the air out of a filled diving cylinder and asked, like, how big would the balloon be that I filled up from this? So the problem-solving strategy essentially is to list what's the same and what's not. So let's just say that this occurs at surface of Earth at about 290 degrees Kelvin, which is really nice of me. I give you Kelvin. Okay. So what happens with the pressure? So the strategy in general for actually any of these is to list what changes and what stays the same and make ratios as needed. So the pressure inside of the tank is 250 bars. And when it's let out, it goes to 1 bar. The volume of a diving cylinder is about 18 liters. So I didn't write that up in the statement of the problem, but I'll just pretend I looked it up. And that's what we want to know. So I have 18 liters of ideal gas at 250 bars, and then at constant temperature, constant mole number, because we don't, lose any, we let it expand until it's all 1 bar. So to be explicit about that, the mole number is constant. We don't lose any particles of gas. We're filling the balloon. And temperature is constant. And if we need it, it's 290 degrees Kelvin. But maybe we don't need it. So I'll start doing this sort of the hard way. And then realize I can just divide out a lot of stuff. So we'll call it P equals initial is same as final, so who cares, R T. And those are the same, so who cares. And then out of tank, PF VF equals N, still the same, R T. And what I realize is I can, if these things don't change, they're a constant. And in fact, because they're the same constant, and I can equate them. So honestly, this problem is just kind of like sneaking Boyle's law in the back door, but that's fine. So I can set up a ratio. Mostly what we care about is the process. And we have 250 bars over 1 bar. So that's final over final. And then V final is the thing we're looking at. And V initial is 18 liters. So basically, we scale up the 18 liters by a factor of 250. And suffice it to say, that's a really big balloon. So that's 4,500 liters. That's a disturbing amount. So that would be, 2,250 2-liter bottles of Coke, which is quite a lot. So let's put this into more normal SI units. And 1,000 liters is 1 meter cubed. So that means that this is 4.5 meters cubed. So that's a little bit more sensible. I mean, that's like, a box about I could not get my hands around it, but I could probably get pretty close. Okay, so too easy. Let's do something that involves some of this mole number stuff, because we haven't really explored that yet. And I can ask a question that would actually require me to dig into what the number of protons and neutrons and the constituent gases in air are, and we'll do that kind of casually. I'll just ask, like, what's the weight of the gas in this classroom? So and there's no process, so we don't have to do this, before and after thing. We actually just literally need to use all the parts of the ideal gas law. And we'll say this is like 12 by 4 by 8 or something, like 8 meters wide, sure. So we'll say this is a 12 meter by 8 meter by 4 meter room. So that's 348 meters cubed. And the pressure is 1 atmosphere, because the window's open, which is 101.3 kilopascals. I'm just going to put everything in terms of SI units, or 1.013 times 10 to the 3 for kilo, 5, 10 to the 5 pascals. So that's really in SI units. And then the temperature is about 20 degrees Celsius. I'm going to be a brat. And essentially what we want to do is we want to find mass, and then we're going to have to convert this mass through mole number of particles. That'll come easy-ish. Turn that into a mass. So this is basically all the digging around you can do, and the kind of questions one could ask involving digging into mole number. So let's start by just finding this and then turning it into mass, because I have most of the parts already. So I have PV equals nRT. Let's use mole number, because that's actually the easiest thing to convert to mass. That's 1.013 times 10 to the 5th pascals. When in doubt, use SI. 348 meters cubed. N is what I'm looking for. R is 8.314 joules per mole Kelvin. And then temperature, 20 degrees, we got to turn that into Kelvin, so 293.15 degrees Kelvin. Right? And this gives me an N mole number of something kind of a pretty big, 15,968.46. The 0.46 is completely gratuitous. So got that. Now the question is, what does that turn into in terms of mass? And again, probably just a reminder, how do I turn and the identification of the substance into a mass? It basically is like how many protons or neutrons there are in the thing. If you have a table and you look up stuff carefully, including the isotope fraction, that's great. Really isn't going to change the answer by, enough precision to really throw anything off, especially like a mastering physics problem. So let's do this the right way. Okay, so percent approximately, it's like 79 and 21, but is 80% nitrogen gas and 20 gas. Ish. Okay. So and we'll call this average, because either there's an 80% chance they'll have the nitrogen mass, 20% chance they'll have the oxygen mass. So 0.8. Nitrogen, what's the mass of nitrogen? So nitrogen has atomic 16, and nitrogen gas is 2 nitrogen molecules. So this is AMU per atom, and this is 2 atoms. Like really pedantic about it. And then there's a 20% chance that we grab a random molecule, and that's oxygen. So oxygen is O2 gas, so there are 2 atoms per molecule. And then oxygen has an atomic number of 16. I'm just picking the most common one. There is oxygen 18 out there. And then math happens, and we get AMU per molecule to be about 28.8 typically. Okay, this is just the number of grams per mole. Right? So this is straight up 28.8 grams in every mole of air. And that's a pretty good number for air. So it's going to be in slightly the wrong units. This number, this 28.8 grams per mole, and multiply it by our crazy big number of moles. I'm going to truncate this a little bit as needed. What's called 15,970. And we're at 450. Or 450. Okay. So there's 460 kilograms of air in this room, which, you know, you can imagine how big this room is, or you've been in this particular classroom. So quite a lot, you know, we just don't notice it because it's bouncing all over and hitting us from all sides, which will be our next topic, basically what is temperature, and an intro to kinetic theory.